Okay, welcome back to chapter 17. Let's move down to the bottom half of page 89, where you see the phrase preparation of alcohols or review. Okay? Let me just tell you that this particular section will not be on exam 3. Okay, not on exam 3. So will it appear on the final? It may appear on the final. That determination still has to be made. So for now though, let's go ahead and go directly to page 90, and we can look at other ways to prepare alcohols. But if you want to do these on your own, these were things that we had back in chapter 8, and if you had me for organic, I provided you with a series of pages that had all the reactions for chapter 8 as well as chapter 9. Okay, that being said, let's move over to page 90. So if you go to the top of page 90, it's going to show us another way that we can make alcohols. And this is a very important section because we're going to be looking at carbonyl chemistry for the balance of the semester. So one way to produce an alcohol is simply by reduction of a carbonyl compound. Okay? So in the case of reduction, we're going to use reducing agents. What does that mean? That we're going to establish carbon-hydrogen and oxygen-hydrogen bonds. Alright, so this is a two-pronged problem in that we're going to see how, first of all, how to convert compounds into alcohols. And then after that, we're also going to look at classifying these particular alcohols as being primary, secondary, and tertiary. Alright, let's take a look at the first one that I have on the top of page 90. You may recall this is an aldehyde that we've actually used in lab. It's called benzaldehyde. Okay, and you may recall these particular reagents as well. Let's take a look at that. This is the two-step process where in step 1 we're using sodium borohydride, and this is ethanol, which is functioning as a solvent. And in step 2 we're quenching this reaction by adding a Bronsted acid. So in effect, we're going to add a hydrogen to here in step 1, then we're going to add a hydrogen to there. In step 2, the overall result is this will become an alcohol. Now, sodium borohydride is a source of hydride. Right? It's a source of hydride. Hydride is a reducing agent. Bronsted-Lowry acids are a source of protons. So you can see the overall effect is we're going to add two hydrogens, one in the form of hydride and one in the form of a proton, to this particular functionality. Well, how does that work? Hydride actually acts as a nucleophile when it separates from boron. So let me just kind of show you a generic perspective on that. Let me sketch a borohydride anion. So here's borohydride. Okay, it would have a formal charge of negative on the boron. And it coordinates to the lone pairs of oxygen. Okay. But what happens is once it gets in the right position, a hydride anion will form a bond to this carbon. Recall the carbon of carbonyls is very electrophilic. So this is behaving like a nucleophile. Subsequent to that, the pi bond will break, and we have an added lone pair on that oxygen. Let's go ahead and sketch the intermediate from this. Now you're not required to show the intermediate, but I want to for explanation purposes. All right. So there's the hydrogen that was already there. Here's the oxygen that now is sp3 bearing a negative charge. And what happened? The hydrogen from sodium borohydride is now covalently bound to this carbon. So that's the reduction step from step 1. All right. Now in a lab setting, you would not isolate this particular species. Okay? Instead, you would quench it with acid. So let me put square brackets around this to indicate that we're not isolating this, that this is an intermediate. We sketch one little arrow here and remind ourselves of what's going on. A Bronsted-Lowry acid is simply a source of protons. Okay? And there would be your Bronsted-Lowry acid, the hydronium ion, H3O+. As you can see, this alkoxide anion is considerably basic, and therefore it would pick up this proton from the Bronsted-Lowry acid. Thus, this is called quenching. You're quenching the overall reaction. So what's the result here? The result of the reduction of benzaldehyde is that you're producing benzyl alcohol. Okay? You're producing benzyl alcohol. Okay? This is called benzyl alcohol. Let me write that down. That's a common name. Benzyl alcohol. Benzyl alcohol. Now it's incumbent upon you to recognize what is the order of that particular alcohol. Well, you may remember that all one has to do is, if you see a methylene, okay, that makes this what? A primary alcohol. So what have we learned? We've learned that the reduction of an aldehyde using this process results in the formation of a primary alcohol. So no matter what the structure of the aldehyde, if you reduce it using sodium borohydride and quench it with acid, you're going to get the corresponding alcohol. Now the next reaction is very much alike. But what's the difference? You may notice here we're not starting with an aldehyde. This is an example of what? This is a ketone. Alright, this is a ketone. But the sequences of steps and the type of intermediates is the same. But what's going to happen here? What's going to happen is you're going to reduce that carbonyl of the ketone by providing a hydride here and a proton there. So let's just go ahead and go straight to our product. Notice we have a 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon chain. I'm going to draw that in as zigzag. And over here, with this carbon, we had a methyl group. But now what do we have? Folks, this has been converted into an OH, and this is now hydrogen. Okay? So we have a methine, which makes this what? A secondary alcohol. So what's going on here? This sodium borohydride reduction followed by acid quench of a ketone gives you what? A secondary alcohol. So these are very mild reducing agents, and they're very effective for converting aldehydes and ketones to the corresponding acids, alcohols. However, sodium borohydride is not strong enough to reduce a carboxylic acid. So let me write this in, that this is the carboxylic acid. carboxylic acid. So we're going to have to use a different reducing agent for that. In this case, we're using a lithium aluminum hydride, which is a very strong reducing agent. I think that's worth remembering. This is a strong reducing agent. Sodium borohydride up above is a weak reducing agent or mild reducing agent. What happens here with the lithium aluminum hydride is that we end up reducing that functionality in its entirety. Okay? Notice too that we're quenching with water, but you just could have easily used acid here as well, so long as you have a proton source. So the overall result by reducing a carboxylic acid with lithium aluminum hydride is that we're going to convert that carbonyl into a methylene. So where you formerly had a carbonyl, you now have a methylene. Okay? So that should be a hydrogen. Kind of messy. Recognize this compound? Right. It's the same as that one there. This is benzyl alcohol, which is an example of a primary alcohol. So see the similarities in the first reaction and this one? The distinction is there we started with an aldehyde, here we're starting with a carboxylic acid, but we need a stronger reducing agent in order to convert that into a primary alcohol. Now, in none of these cases have I shown you the byproducts. Okay, you need not know or be aware or even offer illustrations of the byproducts, but they're there. We would only show them if we had a mechanism. Okay, now look at the last one. Folks, the last one makes use of the same set of conditions, lithium aluminum hydride, a strong reducing agent, and quenching with water. But what's the difference? Here we have a carboxylic acid, and here we have an ester. This is an example of an ester. All right. Now, in the case of this, we're going to get the same results, okay? But I would like to show you the byproduct here, just so you know what became of this particular group here. See, up here we weren't that concerned about that proton, but we have quite a few carbons here. What's going to happen? Well, just as in the previous case, you're going to convert this into an alcohol. All right. So let me go ahead and sketch that out for you. Let me draw that O down like this. There's my pi bond. The pi bond is going to be there. And this becomes an alcohol. So in effect, you ended up with the methylene at this position. Now, what is the fate? What is the fate of this part of the ester? Just in case you're wondering. Folks, that part of the ester becomes ethyl alcohol after the quench. So in effect, this would be your organic product, the one on the left, and this would be nothing more than your byproduct. Here, your goal is to provide me with the structure, okay, of the major organic product. We're not that concerned about the byproduct. Let's flip over now to page 91, because we're going to continue talking about this type of chemistry. Folks, I'm looking at page 91 of your lecture notes, section 17.5. This is a lengthy section, but it's very important. It's one of the most important topics in all of organic chemistry. It's another way to make alcohols. but we're going to do so by conducting reactions of carbonyl compounds. Not that different than the previous section, but here we're discussing the Grignard reaction. Now if we come back to lab, we're going to do a Grignard reaction. If we don't, then we're just going to have to rely on what we're learning here. Okay. So I would say that this is a very important topic. Victor Grignard, he actually won the Nobel Prize in Chemistry for the discovery of this reaction. And what we're going to learn is this is in a category of something called organometallics. Organometallics. Now, just as the name implies, you see the word metal, because there's going to be a metal involved. You don't often see metals in organic chemistry, but believe you me, they're very important. So what is a Grignard reagent? This is a generic representation of a Grignard reagent. Okay, what does that mean? Folks, we're going to have some R group or some carbon group. It can be aromatic, it can be aliphatic. Magnesium in the middle and some halogen on the right. So the bond between the R group and the magnesium is very polar, and so forth. Therefore, this R group is going to act like it's a nucleophile. Okay. Now, you may not remember it, but you actually learned how to make a Grignard reagent back in Organic 1 when we were in Chapter 10. And how did that work? Here's how it worked. You begin with an alkyl halide, denoted by Rx. Then you placed it with magnesium, and this is magnesium metal. It's a metal, and nothing happens. However, if you add an ethereal solvent such as diethyl ether or tetrahydrofuran, you get a Grignard reaction. Okay, what does that mean? It means, without going through a detailed mechanism, that this magnesium becomes juxtaposed between the R group and the halogen. Okay, so this is a Grignard reagent. Now, Grignard reagents are very moisture sensitive because they're extremely basic. Okay, extremely basic. Way more basic than things like hydroxide anion or anything like that. These are extremely basic. Now, the depiction I have here in the square brackets is much more accurate. Okay? In other words, this bond here that we're showing at the dashed is much closer to ionic. Okay? It's not purely ionic, but it's much closer to ionic. So let me just do this. Approximately ionic. So in reality, the carbon bears a negative charge, and the other components here, the magnesium plus the halogen, bear the positive charge. Okay? So what does that mean? That means that in effect, this is going to behave like a carbanion. You don't see that gnat flying around? Okay. So furthermore, that means that this is going to behave as a nucleophile. It's a nucleophile. So all it needs is an electrophile. Okay. Again, this is very similar to what we discussed on page 90. There you were adding hydride as a nucleophile. Here we're going to be adding carbon as a nucleophile. So let's take a look at two examples. And these are the types of things that I would want you to be able to do. Here's our good friend benzaldehyde again. Right? And notice that it has the carbon as part of a carbonyl, and this is an electrophile. So what's going to happen? Folks, when you have the Grignard reagent, okay, let me just draw it like this, because in effect that's what you have. The Grignard reagent itself is going to attack this carbonyl. Right? And by virtue of attacking there, you're forming a carbon-carbon bond. So what would that look like? Let me abbreviate the aromatic ring with the letters pH and show you what the intermediate would look like. So there's our phenyl ring. Here's the carbon that was already there. Here's the hydrogen that was already there. There's the oxygen that now bears a negative charge. We call that an alkoxide. And here is the methyl group that you added from the Grignard reagent in the form of the methide anion. So this is what happens after the preliminary step. Now, this alkoxide intermediate is not covalent, so what do? You do the same thing that you did back on page 90. You quench it with acid. Alright? So acid is going to serve as a quench to place a proton here. So this two-step process resulting in the addition of a methide group as well as a proton. So what have you done? You've gone from an aldehyde to a secondary alcohol. And that's a very powerful thing. So it was the choice of the Grignard reagent that you had here that determined what the outcome would be there. Now, what is your primary responsibility? For now, your primary responsibility would be to fill in this box here. Okay, in other words, tell me the structure that would go there. And we're not concerned at all about the byproducts. Okay, let's look at another example. Here we're going to have a Grignard plus a ketone, only it's going to result in the formation of tertiary alcohol. Okay, this is a common ketone known as acetophenone. You can kind of tell by the name, phenone, that it's a ketone, but you can tell by the structure that it's a ketone. Well, the chemistry doesn't change. It's the same type of chemistry. Notice again, I'm using methyl magnesium bromide. So what is that actually? It's a source of methide anions. Now the mechanism is a little more complicated than this, in that the magnesium is going to be coordinated to the oxygen, but we're just showing the overall results. So what's going to happen here? The methide anion will attack the carbonyl at the sp3 center. This lone pair will become onto the oxygen, and then that's going to result again in another intermediate. The intermediate will look like the one we just saw, with the distinction being we have a different starting compound this time. So there's the phenyl ring, there's the carbon that got attacked, here's the methyl that was originally there, there's the oxygen, it now bears a negative charge, and here would be the methyl group in the form of methide anion that you added by virtue of adding the Grignard reagent. Now again, all that's necessary is that you add an acid, and that'll quench this reaction. So let's think about what happened in the overall process. In the first step, you added a methide anion to that carbon, and in the second step, you added a proton to that oxygen. Now let me make a couple more comments with reference to the acids, okay? Folks, the acids can be things as simple as water, or they could be dilute acetic acid, or anything that's a proton source. One of the more popular ones, because it separates very nicely, is ammonium chloride. Okay, ammonium chloride is a choice acid for quenching Grignard reagents. Okay, so if you're just wondering about that, let's just remind ourselves what ammonium chloride would look like. Ammonium chloride again is an acid, right? So that would be its structure. In any one of these protons, right, any one of these four protons would serve as an acid to quench this negatively charged oxygen that you see over here in this intermediate. So again, what's your responsibility? Your responsibility would be to fill in this box with the appropriate final product. So what happened? Here we had a ketone, and after the Grignard reaction, we ended up with a tertiary alcohol. Up here we have an aldehyde, and after the Grignard reaction, we ended up with a secondary alcohol. Okay? So this gives you a snapshot of the overall results of doing the Grignard reaction, but you can certainly see how powerful it is because we're building molecules up by making carbon-carbon bonds. Anytime that you make a carbon-carbon bond, that's a very powerful thing. Okay, now at the bottom of page 91, I'm showing you a little more thorough illustration of how this all works. Okay, and you need not memorize this, but I just wanted you to see exactly what's going on when you do the Grignard reaction. Okay, so here's a carbonyl. Now this is typically an aldehyde or a ketone, typically. And recall that the carbon as well as the oxygen are sp2 hybridized, therefore this is trigonoplanar. So think of this whole thing as being flat. Okay? That means that the Grignard reagent up here doesn't have any problem finding a surface of that carbonyl. So the very first thing that's going to happen, folks, is that one of the lone pairs is going to coordinate to this magnesium. Okay? Recall that oxygen and magnesium form a very, very nice and strong bond. Okay, so there we go. That's for all intents and purposes, that's a very strong bond. Well, once that coordination happens, okay, we have a formal charge here, but this particular carbon becomes extremely electrophilic. Extremely electrophilic. And what did we already say about the carbanion from the Grignard reagent? That it's extremely nucleophilic. So it should be no surprise that we've set up a beautiful system here whereby the carbanion can attack this sp2 center, and then it's going to become sp3, and one of the pi bonds between the carbon and oxygen becomes a lone pair. So this thing here is called an alkoxide intermediate, right? Alkoxide intermediate. This is what you get after the Grignard reaction is over. Okay? So in effect, this is step one. Okay, in other words, going from here to here, this is step one by adding the Grignard. But what did we do in step two? We quenched it with acid. So in fact, this is step two. Now to make things look a little bit simpler, rather than showing you acid, I just showed water, because water again is a Bronsted-Lowry acid. And that water, okay, can serve as a source of protons by forming a bond between the oxygen and the hydrogen. So the net result is we go from a carbonyl to an alcohol. So it's not essential that you memorize this, okay, but I did want you to at least have an appreciation for how it worked. Okay, now that we have a pretty good glance at how the Grignard reaction works, let's take a look at a few problems associated with the Grignard reaction. I'm going to do that by turning over to page 92. You're going to find this to be very intriguing. Let's take a look at sample problem 17.13. Okay, what is your job? Your job here is to provide both the structure of a ketone as well as the structure of a Grignard reagent that would produce this alcohol. Okay, so that seems like a pretty interesting thing to do. Well, how does this work? Well, let me offer a little recommendation. Okay, the first thing I would do is recognize the order of this alcohol. This is something that we did back when we first started. Folks, this is what kind of alcohol? This is a tertiary alcohol. So what does that mean? That means you have to begin with a ketone. Okay, that's the first thing. But notice that all the R groups are different. We have a propyl group here, we have an ethyl group there, and we have a methyl group here branching off of that quaternary carbon. Okay? Now, what does that mean? That means there's, guess what, 3 different ways to do this problem. So, One way to go about that, okay, is just find any carbon chain, right? Okay, any carbon chain and any other R group associated with that carbon chain. So let me do this. Since I know I need to begin with a ketone, because that's what produces tertiary alcohols, let me circle or highlight one of the R groups, okay? I could have chosen that one, or that one. It doesn't matter. But by virtue of me choosing that one, I'm telling the world that this is going to be my Grignard reagent. Okay? So let's write in our Grignard reagent based upon that ethyl group. So what we need then is ethyl, and notice how I'm doing this, then the metal, magnesium, and then the halogen, bromine. Okay, that's how you do it. It's always the R group, the metal, then the halogen. Now, do you have to use bromine? You can use any of the halogens you want. Doesn't matter. Bromines are more popular, though, in the actual practice of organic chemistry. Okay. Now, the rest of the molecule, in terms of figuring out what ketone belongs in this box, is by looking at the carbons that we did not highlight. Okay? Let me just draw that structure in this box over here, and then we'll work on it. And I'll draw it in the same relative orientation that you see there. So you might notice that we have this propyl group, 3-carbon chain, and then suddenly there's a carbon, and then suddenly there's a methyl group, right? Folks, this needs to be a ketone. What can I do to convert this into a ketone? Simply provide a doubly bonded oxygen. And guess what? You've done it. You've done it. So this ketone here, which is 1, 2, 3, 4, 5, this would be 2-pentanone. Along with this particular Grignard reagent, which is known as ethyl magnesium bromide. Let me write that down. This is called ethyl, okay, magnesium bromide would be the Grignard reagent that you would choose in order to add an ethyl group to this position here of the ketone. So this is perfect. Boom, we got it. Now, since I told you there were 3 approaches, what I've done in the bottom part of page 92 is I've shown you all 3 of those. So what I'd like you to do when you have the opportunity is compare all of these different approaches, okay, to producing a common product, right? Every one of these will give you the same final product. It's just that we have a different ketone and a different Grignard reagent, but they all give the same result. So what you may want to do here is cover up, okay, these as you go, and see if you can fill in these boxes as if they were empty. And if you can do that, then you basically mastered how to work with Grignard reactions. Okay, we're nearly done with Grignard reaction. Let's go a little bit further though. I'm going to flip over to page 93 with you. Alright, here's page 93. Folks, on page 93, we're going to move away from aldehydes and ketones for Grignards. And we're going to look at esters. Okay? Now, esters are different. Okay? They have carbonyls, but unlike ketones, they actually consume 2 equivalents of Grignard per 1 equivalent of ester. So the stoichiometry here is pretty straightforward. Notice that I have this ester, okay? This ester here. And this is called methylbutanoate, an ester. And we only have 1 equivalent of it. Now, if you don't like the word equivalent, you can use the word mole. If you don't like the word mole, you can use the word molecule. So the ratio of here, in terms of the stoichiometry, is that we have 1 mole of ester, but 1 mole of ester will consume 2 moles of Grignard. Okay? Okay. So, what's the identity of the Grignard reagent here? Can you name that one? That's methyl magnesium bromide, right? Well, look at our final product. We end up transferring 2 methyl groups in the form of methyl anion from the Grignard to this carbonyl. And what was the fate of that oxygen? That oxygen that I'm pointing at became the alcohol, right? You say, what's the fate of this? Folks, this particular group here gets broken off. It ultimately gets broken off, and I'll explain that in a little more detail. And it becomes the byproduct, methanol. So, what do we have again? We have an ester over here on the left. We have 2 equivalents of Grignard here as a reactant. And what are the results? What do you get when you react an ester with 2 equivalents of Grignard? What do you get? You get a tertiary alcohol. Okay? Tertiary alcohol. Okay? Alright. Now don't concern yourself with the byproduct, but it's kind of useful because it kind of points in the direction of where all the atoms end up at. Now what I like to do here is provide an explanation using curved arrows for how this worked. Okay? It's really not that complicated. It's just that the nucleophilic attack happens more than once. So let me go ahead and provide you with an explanation of how it is that esters end up consuming, mind you, 2 equivalents of Grignard. Okay. Now to make this a little bit simpler, let me just designate that as R, okay, so that it doesn't take too much time or space to provide an illustration. So in organic chemistry, if you're ever asked for an explanation, okay, we always have to use what? A mechanism. Now I'm going to provide a mechanism that shows you the generic aspects of this reaction. So let's start it this way. Let's first get our ester. Okay, here's our ester. And again, R here is propyl, the propyl group. What's the identity of the Grignard? In effect, the Grignard is what? I'm not going to show all the metals, I'm just going to show the carbanion. We have methyl magnesium bromide, right? What's it going to do? It's going to act as a nucleophile to that carbon. Now it's tempting to think that this methoxy group is going to break off at this point, but it doesn't. It doesn't do that. Instead, we're going to get something known as a tetrahedral intermediate. And that should make a little more sense here in just a few seconds. So now you have an alkoxide. You do. Okay, let me put the lone pairs on there and a negative charge. And here's the first methide group that came from the first equivalent of the Grignard. So I think that warrants writing in. This is our what? This is our first equivalent. Your first equivalent. Okay? And what did I say this was? It's an intermediate, but more specifically, it's a what? A tetrahedral intermediate. Forgot how to spell tetrahedral. There we go. Tetrahedral intermediate. Okay? So you don't isolate it. Now the reason it's called a tetrahedral intermediate, pretty simple. This carbon went from sp2 to sp3, which is now tetrahedral about that center. Okay. Now, at this stage, any one of the 3 lone pairs on the oxygen can collapse in between the oxygen and the carbon it's attached to. And then this group breaks away. Okay? It's going to break off. And by virtue of breaking off, what do you have? Well, let's just look. Do you agree that that group's broken away by me drawing that curved arrow? Okay. So here you are, you have a methoxy group that broke away. Right? Well, what did that make? We have a ketone. Okay, we have a ketone. Let me put some lone pairs on here. I'm going to go back, put some lone pairs on there, here, here. Just so we're a little more accurate. Right? A lot of lone pairs. What's going to happen next? Well, recall that we had two equivalents, right, of a Grignard reagent. So what's that second equivalent going to do? It's going to do the same thing the first one did. Let me just sketch it in. And let me write that down. This is our second equivalent. And in good fashion, it's going to attack this ketone. And what do we learn on page 92 about Grignards reacting with ketones? They produce what kind of products? They produce tertiary alcohols. So, once that's happened, you now have this new alkoxide whereby you've added two methides in the form of a Grignard reagent. And then all that would be left, okay, is to quench this with acid. So there you have it. That's an explanation for how it is that an ester consumes 2 moles or 2 equivalents of a Grignard reagent. Okay? So I understand that's pretty complicated, but if you follow the logic here and kind of see the overall results, it turns out to be not so complicated after all. Alright, we have one more problem to go. And folks, this is a cyclic ester. Okay, this is a cyclic ester. And cyclic esters have special names. They're called lactams. Okay, lactam. This is an example of a lactam. And this is not lactam, it's an example of a lactam, which is cyclic ester. Okay. But the important thing is we have the ester moiety here, okay? There it is. And because we have the ester moiety and we have 1 mole of this, what does that mean? What are the implications? The implications are that we can add 2 equivalents of Grignard per equivalent of ester. So both equivalents are going to go there. Okay, we're going to add methyl here, methyl there to make a tertiary alcohol at this spot. Okay, let me just put an arrow going there to tell you what's happening. This becomes what? Becomes a tertiary alcohol. Okay? Now let's go back up here briefly. Look at that one. What did that become? It became an alcohol as well, right? The byproduct, because it got quenched in acid just the same. So look at that oxygen. Doesn't it break away from the carbonyl-carbon? Well, this one's going to break away as well. So why don't we just put a squiggly line to indicate that this is where it's going to break? It's going to break right there. But this is going to become an alcohol as well. I'm just going to write becomes an alcohol. All that means is after you break it off, you just have to put a proton on that oxygen. It becomes an alcohol, ROH. So without going through a detailed mechanism, let's just see if we can go straight to the product by what we've discovered. Now, let me do it this way. I'm going to draw this a little bit bigger than we normally would do. Okay. There's your oxygen. And here's that part of the ring. So what did we just say? We said that this is going to become a tertiary alcohol because we're going to add 2 methyl groups. Let's go ahead and add our 2 methyl groups. We'll put one like this okay, and one like this, CH3. And that becomes an OH. And what do we say about that one? It also becomes an OH. But you have it. There's our answer. Now, aesthetically, this doesn't look very appealing, but you know what? It's still correct. It warrants all the credit you could possibly hope for. But if you prefer, you can draw it out in a zigzag fashion that looks a little more aesthetically pleasing. Let me go ahead and do that with you. What do we have here? We have a 1, 2, 3, 4, 5, 6 carbon chain, right? Count them again. 1, 2, 3, 4, 5, 6 carbon chain. 1, 2, 3, 4, 6, if I can count. And on this end, okay, on this end we have an OH. So we number over 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and it's at position 5. We have another methyl group, and then there's an OH. Okay, and I'll go ahead and explicitly make these into CH3s. Did I do that right? Let me see. 1, 2, 3, 4, 1, 2, 3, 4. Yep, we got it. Either way you want to do that's fine with me, so long as what we have there has the right atoms and right connectivity. So that does it for Grignard reactions. I know it's something that's really very challenging, but it's very important. It's in the top 10, if not top 5, of the all-time important reactions in organic chemistry. We're going to go ahead and stop there and pick up the rest of the material a little bit later. Thank you.